Hey everyone, my name is Alex Wong, and I'll be presenting unsupervised depth completion from visual inertial odometry. This is a joint work with Xiaohan, Stephanie Tsuei, and Stefano Soatto at the UCLA Vision Lab. An agent localizes itself by tracking visually discriminate feature points in the 3D scene. These points can be produced by the means of structure from motion or simultaneous localization and mapping systems up to an unknown scale. If inertial measurements are available, visual inertial odometry systems, or VIOs, can produce points in metric scale. The figure on the right shows a staircase sequence where the feature points are tracked by Xevo, a VIO system. Because the tracked feature points tend to be visually discriminative, the set of points are sparse by nature. A SLAM or VIO system typically maintains a sparse point cloud in the orders of hundreds of points. These sparse points are sufficient for localization or to estimate the motion of the sensor. However, they tend to be a poor representation of the shape of the 3D scene. Here, the empty space between the points could be empty or occupied by a surface. An agent tasked with navigating up the staircase wouldn't know where to step. This extends to the outdoor driving scenario as well, where points are measured by a lidar, and the agent would need to know that there is a surface ahead and not a pothole. Our goal is to recover the 3D scene by densifying the sparse point cloud. However, any attempt to extrapolate the missing depth values typically fail since there are far too few points to inform the scene topology. Hence, we must rely on the information from the image to fill in the gaps, yielding a cross-modal approach that fuses together images and sparse point clouds to reconstruct the scene. The figure on the left shows an example of the staircase reconstructed by our method. Let's begin by examining the input sparse point cloud. Here, we show examples of the sparse points projected onto the image plane as a range map or 2.5D representation from an egocentric point of view. These examples illustrate the challenge of sparse to dense step completion, which is precisely the sparsity. For example, the point cloud produced by a lidar covers approximately 5% of the image plane, and those produced by a SLAM or VIO system covers only 0.5%, and that is if we're being generous. In reality, the inlier set consists of approximately 50 to 100 points, which amounts to approximately 0.05% of the entire image space. Because the input is sparse, typically only a single measurement will be present within a local neighborhood, and in most instances, none. This renders conventional convolutions ineffective. Hence, previous approaches either relied on very deep models with many layers and parameters, or complex specialized operations to propagate the information from the sparse depth inputs. Conscious of the computational complexity and hardware requirement of previous works, our approach aims to not only improve the quality of the reconstructed 3D scene, but also reduce the model complexity such that it can be deployed on top of VIO system to run in real time. To do so, we propose a simple yet effective approach to approximate the coarse 3D structure, which in turn produces a dense or semi-dense representation of the scene and thereby circumventing the sparsity problem. We begin with the assumption that the world surfaces are locally smooth and are supported on a piecewise planar domain, and that the sparse points exhibit local connectivity, which will allow us to approximate the missing regions with small planes or tessellations. We call this coarse approximation a scaffolding. Here are some examples of scaffolding in real life. Notice that they might not give the exact shape of the scene, but if we simply populate the empty regions with planes, then the scaffolding will give us a rough idea of what the scene should look like. But in order to know where to place these planes, we need to know how the points are connected. Hence, to build a scaffolding, we must first determine the connectivity of the sparse point cloud. In practice, there are many ways to determine connectivity. In this work, we choose Delaunay triangulation, a popular meshing technique. To obtain the scaffolding, we can apply a lifting transform to back project the sparse points from the 2D image plane to 3D and compute the triangular mesh using a convex hull. This process is parameter-free, computationally cheap, and can be done in n-log-n time. And once we have the mesh, we can perform linear interpolation over the barycentric coordinates. And to obtain our scaffolding as a range map, we back project onto the image plane. The resulting depth map is typically dense or semi-dense, hence allowing us to forego the need for specialized network operations to process the sparse inputs. However, it is not perfect. The quality of the scaffolding will degrade with respect to the number of points available, but this is where we bring the image back into the picture. Unlike previous works that aim to map the sparse depth and image directly to dense depth, our approach first approximates the coarse 3D scene with a scaffolding and refines the scaffolding with a lightweight network. By doing so, we alleviate the network from the burden of having to process sparse inputs, which enable us to use a much smaller network than competing methods. To start, given the sparse depth measurement z at time t, we first build a scaffolding to yield d naught. Next, we will incorporate image information into the scaffolding using a lightweight refinement network to produce the final depth prediction d hat. To train the refinement network, we will leverage geometric constraints between the associated image at time t and its temporally adjacent frame at time tau to drive the training process using image reconstruction as a supervisory signal. And to accomplish this, we will first need to compute the relative post g between the two frames. This can be directly obtained from a VIO system, and if the VIO system is not available, one can substitute it with a post network that we can jointly train with the refinement network. Next, we will reconstruct the image at time t using the predicted depth and the relative post between the two frames to yield the reconstruction I hat sub tau. This allows us to construct our loss function, which consists of a photometric consistency term, a sparse depth consistency term, a local smoothness regularizer, and a forward backward post consistency term. We note that our approach is completely unsupervised and only require images and sparse depth measurements to jointly learn depth and pose. Here is a visualization of what our network learns to do. Notice that the initial scaffolding is far from perfect and is missing details for the pedestrian in the left and the street signs on the right. The network first learns to copy the scaffolding and then learns to incorporate details from the image. We can see that the network learns to recover the pedestrian and the street sign over time. We will now show our results on the KITTI dataset, which features the outdoor driving scenario. We propose two models for our refinement network, VGG8 and VGG11. Compared to previous approaches, we reduced parameters by as much as 80% while improving performance by 15% to achieve the state-of-the-art on the KITTI unsupervised depth completion benchmark. Our method is also robust. Despite removing 6 layers from VGG11 to VGG8, which amounts to approximately 3.3 million parameters, our performance doesn't degrade by much. We attribute our successes in both performance and parameter reduction to our approximate and refine approach, which alleviates the network from the burden of dealing with sparse inputs. Here, we show qualitative comparisons with a recent approach on the top panel. Our method consistently performs better on flat surfaces such as walls and roads, as well as thin structures such as poles. On the bottom, we show an example of our depth predictions, colored and back projected to 3D. As we can see from the motion, our method successfully recovers the 3D scene structure. While KITTI provides a standard benchmark for evaluating depth completion on the outdoor driving scenario, there exists no standard benchmark for the indoor scenario. In this work, we propose a new dataset that targets the real-world use case for densifying sparse points being tracked by SLAM and VIO systems, one of the motivations for this work. The dataset is collected using an Intel RealSense and is comprised of 56 indoor and outdoor sequences with non-trivial 6 degrees of freedom motion for a total of 48,000 VGA-sized frames with synchronized depth and inertial measurements. The sparse depth measurements are collected by Xevo, our in-house VIO system that has recently been open sourced. We provide sparse point clouds at 3 different density levels, 0.5%, 0.15%, and 0.05%, which is approximately 100 times more sparse than those provided by KITTI. Here, we show quantitative results on the void dataset at each of the 3 different density levels to study the effects of sparsity. Since our method is directly built on top of a VIO system, we also provide results for the case when pose is directly obtained from VIO instead of the proposed PROS network. Considering different levels of densities, the overall trend is consistent for both models. As density decreases by 10 times, performance of both models decreases by approximately 50% across all metrics. Hence, our performance degrades gracefully with respect to density. Also, we note that training our refinement network from pose from VIO consistently gives better performance. We attribute this to the challenging motion of the dataset, which makes pose much harder to learn. Now, we show qualitative results on the void dataset for both indoor and outdoor sequences. The reconstructions on the right are produced by our system using the sparse point clouds tracked by Xevo. As we can see, despite having far fewer points as input than the outdoor driving scenario, such as KITTI, our approach can still recover the 3D geometry of the scene. And to conclude, in this work, we have proposed an approximate and refine approach that achieves the state-of-the-art on the KITTI unsupervised step completion benchmark. While one of our strengths is in the simplicity of our scaffolding step, one can perhaps leverage more complex topology estimation algorithms to approximate the scene. An interesting avenue, perhaps, is to consider whether it is possible to exploit the natural statistics of large datasets to learn connectivity. We have also introduced the first visual, inertial, and depth datasets. Since inertial sensors are now ubiquitous and typically co-located with cameras in many mobile devices, we hope that this dataset can serve as a platform to foster additional exploration into combining the complementary strengths of visual and inertial sensors, not only for odometry, but also for scene geometry. The dataset has been open sourced and is available via the GitHub link above. Lastly, because of the successes of deep learning models in perception tasks, there is a growing trend to learn everything end-to-end. However, as we have shown in this work, leveraging classical techniques such as meshing to approximate the scene can in fact improve performance and reduce model complexity by alleviating the network from the burden of having to learn everything from scratch. Moreover, we have shown in our experiments on void that there are benefits in combining deep learning with existing perception systems such as SLAM or VIO. Both of these observations lead us to believe that classical techniques and deep learning are in fact complementary. So, there's a long road ahead, but we hope that through incorporating known structure into the learning process, we can bring ourselves one step closer to realizing systems that leverages the strengths of both. For those interested, we have open sourced our code on GitHub and can be accessed via the QR code or the link above.
Hey everyone, thanks for watching. If you're interested in learning more, you can find the links to the paper and code in the description. And if you enjoyed this video, make sure to click the like button and subscribe for more content like this.